So here we go. So we are on 2.15, and we looked at these before, but that box at the top, let's read that box again. In a semi-log plot, one of the axes is logarithmically scaled. In our course, we will only be scaling the vertical axis. With a semi-log plot, where the y-axis is logarithmically scaled, exponential functions will appear linear. Okay? All right, let's look at this example again. Use the features of the semi-log plot, which is the one on the right, of the two pictures there, it's the one on the right. Use the features to justify why an exponential model is appropriate for this data. All right, can someone answer that question? Let's back up. With a semi-log plot where the y-axis is logarithmically scaled, exponential functions will appear linear. Let's look at the picture on the right. Charlie?
Yes, well, it looks like the only thing that's really different about them, like in terms of like the y-axis, is that the right one has its 10 to the something power. The other one's just like regular.
Okay, so it's logarithmically scaled, powers of 10, common logarithms. What is the shape? Not exactly, but more or less. What is the shape of the picture on the right? Isn't it linear? And as the curve continues on, would we expect that linear relationship to continue? So if the logarithmic plot is linear, what does that mean about the data? Exponential. So the question is, justify why the exponential model was a good model to use. The data is exponential because the logarithmic plot appeared linear. Okay? All right, so let's get that kind of set in our mind. If the logarithmic plot appears linear, then the data was exponential. All right, let's look down at example 2. The number of people that have heard the joke T minutes after 2 minutes is graphed on the plot above where the vertical axis is logarithmically scaled. Which of the following functions could be a model for P? So that is a logarithmic plot. What shape is it? If you connected those dots, what shape would you have? A line? So if the logarithmic plot is linear, that means the data was exponential. So when I look at my possibilities, it's not A, because A is linear. It could be B, because that's exponential. It's not C, because that's logarithmic, and it could be D. So is everybody good? We got it narrowed down now to either B or D. Okay, how are we going to decide which one it is? Plot a point. Find it once, see which one works. So it looks like if I put in 0, I'm supposed to get 1. So which of those equations, if you put in 0, do you get? Oh, not 1, 2, I get 2, I'm sorry. If I put in 0, I get 2. Which of those equations gives me a 2 when I plug in 0? Not B. D. Just to be safe, let's try another point. If I put in 1, I should get 4. In problem D, or equation D, if I put in 1, do I get 4? Yeah, so I think D is your answer. Does that make sense to you? Got it? Alright, let's look at the next box. Important note. When we logarithmically scale the vertical axis, we're not changing the actual y values. We're just plotting them differently. To logarithmically scale the vertical axis means that equally spaced values on the y-axis are proportional, whereas equally spaced values on the x-axis are linear. So, we have a table of values. We have 4 different graphs there. Which one of those could represent a semi-log plot of this data where the vertical axis is logarithmically scaled? What is your thought? I heard somebody say something. D. D. Violet thinks D. Well, Violet thinks it's D, so that means that if I plug in 1 for X, I need to get 40 for Y. So let's look at picture D. If you put in 1, you got a dot up there. Now, do you remember how these things work? Remember, between 10 and 100, your notches are tens. So it's 10, 20, 30, 40, 50, 60, all the way up to 100. So if you put in 1, do you get 20, 30, 40? You sure do. I think she's right. What do you think, Will?
I was just gonna ask, are the other ones even like logarithmically scaled?
The B could be, but points don't match up. The rest of them are not. Good observation. Yeah.
So like for C, like the points match up, but since it's not.
Logarithmic, look at the y-axis. Remember, on the y-axis, if you're logarithmic, the labels have to be proportional. So 50 to 100 to 150, that's linear, right? They're going up by 50. In D, you are timesing by 10, yeah. And that's the key. That's what Will was saying. Okay, we all right with that? All right, example 4. Can you plot these points on that coordinate plane? Take a second with your partner, plot those points. I'll plot them and then we'll compare notes. Where is Y 200? The first line above 100, right? Because there you're counting by hundreds. 100, 200, 300, right, okay. Let's make sure we're getting started right. How do you do? You compare notes with your neighbor. You look okay? You guys compare notes? You doing okay?
You're right. Oh, yeah.
How about you guys? Got them? Avery, you got them? That's your, everybody comparing, just gonna have you guys figure it out. Right? Last year, I think at the entire exam, there was one logarithmic dot question. So this isn't a huge deal, I don't wanna make a big deal about it, but you got yours.
My packet's a little bit. I actually don't know if I have the last page. I think mine might end it too.
Yeah, you don't have the last pages, so they're canvas.
Okay, yeah.
Pull them up and pull them up.
Okay.
Okay. All right, so now we got one more to go. Here we go, last thing. Given the exponential model, the corresponding linear model is given by this. See, I want you to notice something. That if we start with an exponential, and we take the logarithm of both sides, we'll come up with what he has there in his notes. All right, now tell me about the logarithm of a product. These two things are being multiplied. So what happens when I take their logarithm? I add them. So it's going to be log A plus log B to the x. Now, I am doing base 10 just because I'm too lazy to write another number in there. But could these all be base 7s or base 52s or something? Yeah, I'm just doing base 10. Now, what happens to the x? It comes out in front as a coefficient. Now, assuming A and B are numbers, okay, this is just some decimal, right? And this is some decimal. So isn't that y equals mx plus b? So that's what he's saying here in that box. It says the corresponding linear model is given by this equation, where this will be the slope of the line, and this will be the y-intercept of the line. Okay, let's see what it says for problem 5. Write an equation for the linear model for this plot. All right, let's get some points. What are a couple of points on this thing? Because if I'm going to write the equation of a line, I need a couple of points, right? So what are a couple of points from that plot? 140. And might as well use 260. Right? But I need you to remember something. I have logarithmically scaled my y's. So instead of 140, I'm going to have to think about it as log 40. Remember, the y-axis has been logarithmically scaled. So as I am writing equations for that, using the logarithmic scale, I am going to have to think of my y values as logarithms. Notice in my equation, he uses y prime, and I don't like that too much because I get my y's confused. But in my equation, notice that the y is log, but the x is not, right? That's a regular x, which is exactly what we expect, because the x-axis is linearly scaled, but the y-axis is logarithmically scaled. All right, let's find our rate of change. That would be our slope. What will our rate of change be for these points right here? Average rate of change, here we go. Log 60 minus log 40 over 2 minus 1. Now, I know this is kind of wild, but you just wait. Just hang on, be patient. All the pieces are going to come together, and you're going to be like, oh my gosh. All right, tell me about log 60 minus log 40.
Don't you divide it?
You divide it. So that would be the log of, let's see, 60 over 40 is 3/2. So really, my rate of change, I don't think I need this in there. Oh, maybe I do. Oh well. My rate of change is going to be the log of 3/2. Okay, now wait a second. Isn't that the slope? So don't I now know B? B is 3/2. Okay, what now? I have to find A? Okay, so how do I do it like when I'm doing regular math? Once I find my one variable, how then do I find my other one? Plug it in. So if I plug it in, let's see, here's my equation. Log y equals log A plus x log 3/2. I'm plugging into this equation right here. You okay with that? Now I need one of my points, so I erased them, but wasn't one of them 140? I'll just use that one. So the log of 40 is going to equal the log of A plus the log of 3/2.
Why would it not be the log of log 40? Because don't you have to.
Good question, but I already put that logarithm in.
Okay.
It's already in there. So that's the original y.
Yeah.
All right, so log A is going to equal what? Log A is going to equal log 40 minus log 3/2. What do I do with that?
Divide.
So log 40 over 3/2 equals log A. What's 40 over 3/2? 80 over 3. So log 80 over 3 equals log A. So what's A? 80 over 3. And you just did part B. You just found A and B. Now, I will be, so your equation is going to be log y equals log 80 thirds plus x log 3/2. Now, no one in their right mind, I don't think, is going to do all this to find A and B. We found A and B. Instead, what if we took our original 2 points, just forgot the logarithm part, just forget it, take the original 2 points, and wrote the equation of the exponential. So 40, I'm doing the exponential now, not the logarithm. So 40 equals a times b to the first. And 60 equals a times b to the second. Would you agree with that? So 40 over b equals 60 over b squared, if I solve for a. Oh my gosh, what is b gonna end up equaling? 3/2? And if b equals 3/2, what is a gonna end up equaling? 80 over 3? So it's all the same. It's just doing it the hard way, which you followed directions, did what we were supposed to do, but it came out to be exactly what it would have been had we done it exponentially. Which is further evidence that exponential data is linear when it's on a logarithmic plot, because that's a linear equation, mx plus b. Lord, is your mind sufficiently blown? Probably. Probably. So let's do something more fun. Sometimes we have to just digest things a little bit. All right, friends. We gotta wrap up Unit 2. Let's work through some of this together. We'll work through this together, and then I will give you another sheet, and you can work on that with your teammate. Okay, here we go. Let's all focus in, take good attention. Here we go. The exponential function is defined by this. Which of the following is true? I can't do this without a sketch, so I'm going to figure out what this looks like. And I know what exponentials look like, but I really have to know about this right here, because it matters if that is bigger than 1 or less than 1, right? So let's talk about that. E, approximately 2.7. Pi, approximately 3.1. So this guy right here is a number that is less than 1. So that means, remember, I know what exponentials look like. That means it's a decay. And now I can probably answer the question. Which one do you think is the option? C. C. What is rate of change? Rate of change is another way of saying slope. And if you look at that, the slope is negative. Isn't that curve going down? Now, I'm not talking about the change in the rate of change. I'm talking about the actual slope. And it's negative. That curve is also concave up. So C is the answer. Since it's concave up, the rate of change, the change of the rate of change is actually positive. Increasing, but not the slope itself. So C is the answer. Good job. All right, the graph of the piecewise function is shown. Let f be the inverse of g. Okay, so g is shown. Question number 2 says, what's g of -2? Okay, so what do we do first? Find g of -2? Remember, the picture is g, so use the picture to do g. So g of -2 is 1. So now we're going to find g of 1. And g of 1 is -1. So the answer to that one is also C. Is that all right? All right, the next one says find f of -4. So I want to know f of -4 equals something. There are a couple different ways you can go on this. Be careful, that is not f. That is g, right? But g is the inverse of f. So doesn't this mean that g of something has to give you -4? Well, can I figure that out? G of what would give me -4? 4? So the answer to the problem is 4 or D. Good. The minimum value of f. Now, what we mean by that is what? The lowest y value that we have. So how are we going to do this? The lowest y value of the inverse, Charlie?
Would be the lowest value of the graph of x, right?
Yeah. Wouldn't it be the lowest x value? Aren't we flipping the ordered pairs? So what's the answer? -5. Very, very good. Very, very good. All right, number 5. What would this look like if you had to just write one logarithm? So log one thing. What would be in there? So, go ahead, Parker.
What about y to the half, times
So Parker is suggesting that first of all, we take care of these exponents, so is that okay with everybody? Right? Now, what does a subtraction mean? We're gonna have a division, so we're gonna have x cubed over a y to the 1/2, which could also be written as the square root of y if you like that better. And then what are you gonna do with that guy? He's being multiplied, so he's gonna show up in the numerator. Remember, these two could be switched. So then it becomes really clear that these are in the numerator and he's in the denominator.
Could you put this into the 5, like, still in the parentheses, but off to the side, like in front?
Like over here, like times that. You could, but it's probably better to make it one piece.
Can you
have, like the y to the 1/2, can you put it like that, or do you have to,
Rationalize it?
Rationalize
You
it?
don't have to rationalize it, but you could, and it wouldn't be wrong if you did, but you don't have to.
Okay.
Okay? That is gonna be a multiple choice question, and so you just wanna make sure you match the answer. So if they've rationalized it, rationalize it. If they haven't, leave it that way. All right, now, we gotta get this under control. First of all, when we say end behavior, we are using limits, right? And traditionally, in the majority of cases, I'll call this Y, I'll call it SX. In the majority of cases, we're gonna have the right behavior is gonna be as X approaches infinity, and the left behavior is gonna be as X approaches negative infinity. That is just the basic setup. Now, we're gonna have to modify it a little bit because this is a logarithm. And remember, logarithms don't go both ways. They have an asymptote. So this one's not gonna make sense. We're gonna have to modify that, but this is the typical setup. Everybody okay with that? All right. Again, I can't do this without a picture, so I'm gonna draw a quick sketch. And I'm gonna remind myself, and someday you'll be old like me, and you have these things to remind yourself. I remind myself that this is my standard logarithm. That's what it looks like. Putting a negative coefficient in front of anything does what? Turns it upside down. So this guy gonna look like this. But then, adding something to my X value is going to do what? Shift me left 2. So now, after all this messing around, I'm going left 2, so my asymptote is gonna be at negative 2. My intercept is gonna be at negative 1, and it looks like this. So I'm gonna erase all this so I don't get confused. So this is my picture. Are we good with that? Now, can I go to infinity? Absolutely. This thing, there's the arrow. What happens as I go to infinity? I'm going down. Can I go to negative infinity? No, there's a wall here. Negative infinity is over here. So my limit is not going to be negative infinity. My limit is going to be negative 2. And I'm going to put a little plus sign there to remind myself that I'm going to the left toward negative 2 on the positive side of negative 2. And what's happening when I do that? Positive infinity. Yeah. Now, does anybody have a question about that? All right, take a moment and do the. It's an exponential, so it's not gonna have that shape, it's gonna have a different shape. But logic it out, what's the thing look like? first thing you did with it? When you looked at this problem and you gotta figure out its end behavior, what was the first thing you did? Flip that over. We don't like that negative exponent, so we'll flip that over and make it 5/3 to the x. Now, I know we could combine that, simplify, it, make the exponent x plus 1. We don't need that because that tells me everything I need to know. This number is bigger than 1. That number is positive. So isn't this just going to be a straight exponential? And since exponentials don't have walls, no asymptote, oh, they have no x problems, then we can do our normal end behavior rotation. To the right, did you say positive infinity? And to the left, you said 0. Absolutely, we're getting closer and closer to 0. Anybody have a question about that? Okay, then question 7 says, describe the rate of change. So I went ahead and sketched this one back up here. This was A. Tell me about the rate of change there. The rate of change is negative and increasing. Why is it negative? Because we're going down. Why is it increasing? Concave up. Process for a second. Negative, increasing. All right, how about the exponential? What's happening there? Rate of change is positive and increasing, concave up. All right, number 8, which of these are equivalent statements? So can you find any matches in there? And while you're working on that, I'm gonna go ahead and hand out another review sheet.
Oh. Wait, why would that not be one?
All right, did everybody get a second review?
No, I think it's like this. If you just put this together, no, you put that.
Done that yet, so I don't know if there's any matches or not. Did you come up with anything? one so we can talk about it. Anybody find any that match? Caitlin, what'd you find?
1, 3, 5, and
Whoa.
7.
1, 3, 5, and 7. 1, 3, 5, and 7. She says all match. What do the rest of you think? 9 is 3 squared. So you have 3 to the first times 3 to the 4x. Is that right there? Sure is. So she's right on that one. And what about this one? What's 81? 3 to the 4th. Won't that also be 4x plus 1 on that exponent? Remember, you add the exponent. And this one? Yep, she's exactly right. Anybody find any others that match? What's 243? 3 to the 5th. So isn't this one 3 to the 5x? So won't he match this one? And that one's all on his own because he's 3 to the 6x. 3 cubed to the 2x, so 3 to the 6x. Good? All right. Now, to do the last problem, we have to have the sheet that just, it's this one. It's the one that's my handwriting. This is what we're gonna call review one. I didn't call it that, but that's what we're gonna call it now. This is review one. So if you look at problem 18, or 17, I mean, problem 17 on review one, it is a big giant table of values. And in order to do the one on that second, on that sheet we were working on, we have to do problem 17. All right, so you might as well go ahead and get started on it. It's gonna take a while, but do problem 17 exactly what it says. Here's the x's, here's the y's. Use the logarithmic regression to fit the model for the data. Notice x is defined, 1 is 1995. So 2 would be 1996, and so on and so on. All right, so I need a calculator. This is gonna take a while. But in order to find the residual, we're gonna have to do this.
Yeah, like you can read. Yeah. No, you don't get it. Because you don't have to change.
Make sure you get all these. Wait, are you on a trip? We should go. Not already. It's actually fire. So it's I still want.
Wait, what? I guess.
I do anything else, I wanna double check my numbers with you. What did your equation look like, your logarithmic equation? Y equals 12.704 plus 28.520 ln x. Oh, good, okay.
No, it's not.
So if I wanna find, the percentage in 2013, I am going to let x be 19? And I got 96.680. 96.680%, or, percent. We okay with that?
For which one?
For part B? 17B? Did you not get that, Charlie?
Oh, I'm doing 9, like I'm doing 5, 7.
Oh, yeah, I haven't gotten that there yet.
Oh, wait, so
I did problem 17 first.
Oh.
What did you say B was?
Caitlin,
What did you say B was?
I got 96.680. I don't know if that's right or not, is that what you got?
Yeah, I just wanted to
Okay.
make sure.
All right, now 2000 was 1, 2, 3, 4, 5, 6.
This is the year, yeah.
Did anybody find the residual?
Residual.
What'd you get, Charlie?
0.00515%.
Exactly. So what, and I love that you put a unit on that. So what does that mean? His residual was negative 0.0051, or negative 0.005. What does that mean? The residual is negative. What does that mean? The model overestimated.